we are from Group A and we are going to present our assignment. I'm going to talk about the introduction. So first, Brownian motion described as random movement of particle suspended in a fluid resulting from their collision with the fast-moving molecules in the fluid. Brownian motion is used in many fields such as pure and applied mathematics, economics, physics, and also biology. Some of the application of Brownian motion in stochastic process are as a limit of random walks, transition probabilities, and also symmetries and scaling laws.
Okay, I'll be explaining about the method used in this study. For this spread of disease, infected susceptible can be described the following differential equation has been shown, where the ST denotes the number of susceptible and IP denotes the number of infected patients, where the mu is the per capita rate and the rate of infected individuals being cured is denoted by the gamma, where beta is the coefficient for the disease of transmission. The next SDE is followed in the previous equation, the second one, where it's written in the differential form where the dt is taken to the other side. So the beta still represents the rate at which the infectious individual makes contact with another infectious patient who are susceptible. Suppose the stochastic environment factors acts on each individual who are affected in the population. The beta changes to the random variable beta. Each infected individual then makes a new equation as the following, where Bt represents the Brownian motion and dBt is the increment of the Brownian motion. By the central limit of theorem, the total number of potentially infectious contact made has approximately a normal distribution with mean n mu naught and variance n standard deviation square. Bt in the equation, the previous equation, is replaced with this equation to obtain the following one, where Bt denotes the mean of stochastic number potentially infectious contact, that is infected individuals makes contact with another infected individual. The deterministic SIS model from the previous equation, the first equation, becomes the Ito SDE. So the following SDE SIS model, given that the infected person and the susceptible person equals to n, which is the total number of people involved, is sufficient to study the SDE for number of infected people. So this is the equation, the Ito equation, which should be used throughout this whole study, where the starting number of infected person is equals to 0. So that means the date rate is at time 0.
Now I'll introduce about the results. The spread of disease can be divided into few classes such as susceptible, infected, and removed individuals. An individual becomes susceptible at first, then they are infected by a disease. Then they will become permanently immune to their disease. This is called Hema-Kendrick model. It is also called the susceptible infected removed model. First, consider for any given initial value will equals to I0. The SDE model will have a unique global solution with probability 1. Then we'll get this equation. Then we'll set tau infinity equals to limit when k tends to infinity tau k. If tau infinity equals to infinity, then tau e will equals to infinity also. By using the Ito formula, we'll get this equation, where LV equals to this equation.
Good day. So for the continuation of the result, we use the SDE, which is this equation showed here. Next, we consider the basic reproduction number for the stochastic model, and this equation is shown by equation 1.10. And then for any given initial value, I0, the solution obeys the equation 1.11. So then we solve this equation using Ito formula, as we can see in equation 1.12 and 1.13. Next. Okay, so this implies the equation 1.15. As you can see, we find the limit for the log IT. And by the large number theorem of Martingales, we can see that for the classical deterministic SIS model, the IT tends to 0 if and only if the basic reproduction number for the deterministic model is less than or equal to 1. And for the SDE SIS model, we can see that IT tends to 0 if these two equations are satisfied. Next, we can consider the equation 1.16. We find the limit and integrate it from t0 to t. And this shows that the conditions for IT to become extinct in XDE SIS model are weaker than in the classic deterministic SIS model. Thank you.
Hello, I want to talk about a conclusion. This model is used by some researchers to state about the diseases that have been transmitted by bacteria and have no immune system. It continues traditionally for epidemics, and it based on common differential equation. And for human disease, its nature of epidemic growth and spread is inherently random. The variability and randomness of the environment is fed through to the state of the epidemic. Thank you. That's all for our assignment.